In many plant processes, certain physical conditions are subject to change. These changeable conditions are called process variables, and four of the more commonly monitored ones are pressure, temperature, level, and flow. But there's another group of process variables that are also commonly monitored in plants. They're called analytical variables. Analytical variables are based on the physical and chemical composition of materials. As with other process variables, it's important to understand how analytical variables can affect processes and how they're measured. Measurements of analytical variables provide operating personnel with valuable information about process materials before, during, and after a production process. Closely monitoring analytical variables is vital to producing an acceptable product. In fact, the general purpose of measuring analytical variables is to ensure that process requirements are met. For example, in a process where two substances are combined to form a solution, it's important for the proper proportions of the substances to be used. Closely monitoring the analytical variables associated with the process may prevent deviations that could lead to a defective product. Many analytical variables can be measured in industrial processes. Five of the more commonly measured ones are concentration, which is the amount of one material dissolved in another material in a solution; density, the weight per unit volume of a substance; clarity, the measure of how clear or transparent a substance is; humidity, the measure of how much water vapor there is in the air; and moisture, the measure of the amount of water in a solid material. By monitoring these and other analytical variables, operators are better equipped to control plant processes. Analytical variables are of value to operating personnel only if they can be accurately measured. Analytical variables are typically measured using instruments called analyzers. An analyzer measures and indicates physical or chemical characteristics that are based on the composition of a material. Analytical measurements can be obtained in different ways. One way is to take or grab samples from a process periodically, and then analyze them in a laboratory. Another way is to monitor analytical variables continually. In either case, analyzers help ensure that product requirements are being met by monitoring characteristics of raw materials going into a process, changes that occur within the process, and characteristics of final products. For example, this clarity analyzer is used to make sure that a liquid going into a process is relatively free of contaminants. This pH analyzer is used to monitor the pH of a solution during a process. And this moisture analyzer is used to make sure that the moisture content of this final product is acceptable. Besides ensuring that product requirements are met, analytical measurements can also help keep the workplace safe. For example, an analyzer can be used to determine the concentration of oxygen in a confined space so that personnel will know if breathing gear is needed. Analytical measurements can also help protect the environment. For example, analyzers can be used to monitor waste gas that's being released from a stack and waste water that's being discharged into a lake or river. In this topic, we identified some of the more commonly measured analytical variables, and we talked about why and how they're measured. Now let's try some practice questions that relate to this material. Many analytical variables can be measured in industrial processes. Five of the more commonly measured ones are concentration, which is the amount of one material dissolved in another material in a solution; density, the weight per unit volume of a substance; clarity, the measure of how clear or transparent a substance is; humidity, the measure of how much water vapor there is in the air; and moisture, the measure of the amount of water in a solid material. Analytical variables are typically measured using instruments called analyzers. An analyzer measures and indicates physical or chemical characteristics that are based on the composition of a material. Sometimes it's important to know the relative amounts of the substances in a solution. One way to do this is by determining the concentration of the substances. Concentration is basically the amount of one material dissolved in another material in a solution. A solution is a homogeneous mixture. That is, two or more substances, such as liquids or gases, that are evenly dispersed in each other. For example, these two beakers contain homogeneous mixtures of dye and water. But as you can see, the solution in the beaker on the right is darker than the one on the left. That's because the solution on the right has a higher concentration of dye. Concentration measurements can be expressed in different ways. Two ways that are commonly used are percent measurements and parts per million, or ppm measurements. Percent measurements express the amount of a material per 100 parts of total solution, either by weight or by volume. For example, if this solution of water and dye contains 10 ounces of dye, and the total volume of the solution is 100 ounces, then the concentration of dye is 10 parts per 100 parts of solution. 10 divided by 100 is 0.10, or 10%. So the concentration of dye is 10% by volume. Parts per million measurements express the amount of a material per million parts of total solution. 10 parts of dye per 100 parts of solution is the same as 100,000 parts of dye per 1 million parts of solution. The concentration of the dye, then, is 100,000 ppm. As a general rule, parts per million measurements are used for measuring very low concentrations of materials in solutions. Adding substances to liquids is common in many plant processes. When certain substances are added to a liquid, electrically charged particles called ions are formed. When this happens, the concentration of the substance in the liquid can be determined by measuring the liquid's ion concentration. The ion concentration of a solution can be determined by measuring the solution's pH. Specifically, pH is a measure of a solution's hydrogen ion concentration. In general, though, it's an indication of a solution's acidity or alkalinity. You see, acid and alkaline solutions contain hydrogen ions and hydroxyl ions. A hydrogen ion is a positively charged hydrogen particle. A hydroxyl ion is a negatively charged particle made up of oxygen and hydrogen atoms. The acidity or alkalinity of a solution depends on its concentration of hydrogen and hydroxyl ions. For example, an acid solution has a greater concentration of hydrogen ions than hydroxyl ions. The stronger the acid solution, the greater the concentration of hydrogen ions. An alkaline solution, or an alkali, has a greater concentration of hydroxyl ions than hydrogen ions. The stronger the alkali, the greater the concentration of hydroxyl ions. Pure water is neither an acid nor an alkali. In pure water, the concentrations of hydrogen ions and hydroxyl ions are essentially equal. Since there is no majority of either type of ion, pure water is said to be neutral. The acidity or alkalinity of a solution can be expressed on a pH scale, such as this one. On this scale, pure water is assigned a value of 7. From 7, the numbers on the pH scale increase to indicate increasing alkalinity, and decrease to indicate increasing acidity. For example, a strong acid like sulfuric acid might have a value near 1 on the scale. A strong alkali like caustic soda might have a value near 14 on the scale. Now, one thing to remember about the values on a pH scale is that they can be misleading if they're taken at face value. That's because between any two adjacent numbers on the scale, the concentration of ions changes by a factor of 10, not by a factor of 1. For example, a solution with a pH of 1 has 10 times more hydrogen ions than a solution with a pH of 2. In some applications, it's possible to determine the concentration of a substance in a solution using the solution's pH. But to do this, you first have to be able to measure the pH. One way to do this is to use a device called a pH analyzer. The pH analyzer represented here has two electrodes which are submerged in a beaker of solution. The electrodes and the beaker of solution form what is known as an electrolytic cell. The two electrodes are connected by wires to a measuring device that has a pH indicator. The principle of operation for this pH analyzer is based on the fact that the electrolytic cell will produce a voltage in relation to the pH of the solution. The voltage output from the cell is then amplified by the measuring device and displayed as a measurement of pH. pH analyzers are used in many types of industrial processes. For example, they're often used for monitoring and controlling the pH of materials involved in chemical production processes. They're also commonly used to protect process equipment. For example, pH analyzers help prevent the water in this cooling tower from becoming too acidic or too alkaline and corroding equipment such as pumps and piping. The ions that are present in a solution have an important characteristic: the ability to conduct electric current. The ease with which electric current flows through a solution is the solution's conductivity. As the concentration of ions in a solution increases, that is, as the solution becomes more concentrated, its conductivity increases as well. For that reason, the concentrations of some solutions can be determined by measuring their electrical conductivity. This simplified illustration shows an electrical conductivity measurement system. The system includes a conductivity cell, which consists of a pair of electrodes or probes surrounded by a shield, and two wires, which connect the electrodes to an electrical conductivity meter. During operation, an electric current passes through one probe, then through the solution being measured to the other probe, and back to the meter. The ease with which the current passes through the solution is measured and displayed as an indication of the solution's conductivity. In this arrangement, the conductivity value is indicated on the meter scale. But in some systems, the measurement is sent to a recorder where a permanent record of conductivity values can be maintained. Now suppose we put a different solution in the beaker and repeat the test. But this time, the pointer doesn't move as far up the scale. That's why the pointer didn't move as far up the scale, because the conductivity of this solution is lower than that of the previous solution. Now, the way a conductivity measurement is expressed can depend on the units of measurement that are used. For example, ion concentration is sometimes expressed directly, either as a parts per million measurement or as a percent value. But electrical conductivity can also be expressed using a basic unit called the mho. A mho, which is ohm spelled backwards, is the reciprocal of an ohm. While an ohm is used to describe a substance's resistance to current flow, a mho is used to describe a substance's ability to conduct current. Many conductivity analyzers use units of micromhos. A micromho is 1/1,000,000th of a mho. But regardless of the scale that's used, conductivity measurements can serve a number of purposes in industry. For example, they're commonly used to check for dissolved solids in boiler water, which can cause scale buildup in boiler tubes. Dissolved solids increase the water's conductivity. If conductivity measurements indicate that the water has a high level of dissolved solids, operating personnel can change treatment procedures to prevent scaling in the boiler. During this topic, we talked about what concentration is, and we focused on how to determine liquid concentrations by using pH measurements and conductivity measurements. Now let's try some practice questions. Concentration is basically the amount of one material dissolved in another material in a solution. A solution is a homogeneous mixture. That is, two or more substances, such as liquids or gases, that are evenly dispersed in each other. For example, these two beakers contain homogeneous mixtures of dye and water. But as you can see, the solution in the beaker on the right is darker than the one on the left. That's because the solution on the right has a higher concentration of dye. The acidity or alkalinity of a solution can be expressed on a pH scale, such as this one. On this scale, pure water is assigned a value of 7. From 7, the numbers on the pH scale increase to indicate increasing alkalinity, and decrease to indicate increasing acidity.